Hello and welcome to Lecture 5. In this lecture we're going to cover section 2.4. This is going to be the last section that we cover in chapter 2, so this is the final lecture for chapter 2. All right? It's the third of 3 lectures that cover chapter 2. In this one, in this lecture, we're going to discuss free fall. All right? Now, free fall is really just another case of constant acceleration, so you're not going to see much new material here as compared to the previous lecture, lecture 4. So it's kind of more practice with constant acceleration. But it's a very important system. It kind of comes up a lot when we talk about real life situations, so it deserves its own lecture, in my opinion, okay, for this particular class. So let's just define free fall. So free fall is just vertical constant acceleration motion, right? That's what I mean, but there's nothing new here. All right, it is motion when the only acceleration on a particle or object is gravitational acceleration. And gravitational acceleration is defined as 9.8 meters per second squared. That's kind of like a global average. It obviously is a number with just 2 significant figures, but not really. So I would never consider it to restrain the number of significant figures in a problem. If all the other values had 4 significant figures, then just assume that this is 9.800. Get it? And it does have some big assumptions built into it. It ignores air resistance, variations in G, because G does vary just because of the continent you're on. It varies because of your latitude, and it varies because of your altitude above the ground. All of those are ignored. We just take it as 9.8 on average. So if you look at our key formulas, they should look really similar to the ones we've seen before. Right? So these are just the big 3 of the kinematic equations, but now they're just specific to free fall. Well, how so? Because we've replaced A with negative G for every one of them. See, this used to be plus A, now it's minus G. Okay, this used to be plus 2A, now it's minus 2G. Now, in putting the sign into the equations, we are making an assumption that our coordinate system defines positive y as upwards. Because G can be positive, in that case, we're just defining positive y as downwards, okay? But for most of the time, this is the case. And so I'm saying that for that utility, for the problems where you can define positive y as upwards, then you can get away with just writing the equation like this, with minus G, okay? Or you could even just stick to always defining positive y as upwards, except sometimes it's really convenient to define it as downward. It can save you some algebraic trouble, okay? So really 3 types of problems, right? So we have kind of basic problems where you just use a single kinematic equation and you want to kind of have some basic knowledge of free fall to help solve them. For example, velocity is momentarily 0 at the top of a toss, because it has to change direction, thus it must momentarily be at rest at the very top. All right? Fairly complex problems involve using kinematic equations of free fall for more than one object. All right? And then fairly complex problems that involve combining the kinematic equations with the constant velocity of sound. So kind of specific, but it's its sort of own category of problem. So you drop something, you have accelerated in a free fall, and then maybe there's the sound of the impact of that something hitting the ground, and that sound has to travel back up to the person that dropped it, for example. That's the example we have. And so that idea of having sound travel as sort of the signal of when something gets somewhere is kind of an interesting problem in its own right, and we can just think about how we would solve it. All right, so let's start with a very simple problem in 3 parts. You throw a ball straight up with an initial velocity of 15.6 meters per second. How much time until the ball is momentarily at rest? Well, we know, if you think about free fall, that it is momentarily rest at the top, okay? So let's think about this, right? So at the top of the toss, we don't need that information yet. But we can just set it up like this. We're just going to use our kinematic equation for velocity as a function of initial velocity, acceleration, and time, all right? And we know that it's 0, initial velocity is positive 15.6, gravity is negative 9.8, solve for t, and it's 1.59 seconds. So what that represents is the time for our ball to get to the top of the toss. It takes 1.59 seconds to get up there, okay? What is the maximum height reached by the ball if we take the initial height as 1 meter above the ground? Okay, so now we're going to use the time we solved for, right? Set up a displacement equation in the vertical direction. All right, we've got our initial 1 meter, our initial velocity, our time to get to the top, right? Because now we know that the time we solve for must be the time to get to the top. All right, so see how they didn't, because otherwise it's like, how do we even know what the top is, right? Well, we know it's achieved after 1.59 seconds. All right, and so then we end up with 13.4 meters. Okay, and then how long does the ball spend in there? So here I'm going to assume it's caught at the same height it is thrown at. So it's essentially going to go, start at 1 meter and come back down to 1 meter. So in that case, it's just double the time to get to the max. because it goes up to a particular max height, and then it comes back down. It spends equal time coming down as going up, so we can just double 1.59. So we can say the time of flight is just twice the time to get to the top. Okay? So that's kind of what I mean by the kinematic assumptions, the kinematic shortcuts you can take in free fall problems. All right? And yes, it's free fall when it's moving up. All right? It's a good point to kind of stop and realize that. Free fall isn't just things that are falling downwards. Something that's going up is still in free fall because it's slowing down the whole way on the way up because the acceleration is downward and is gravity. Okay? So let's fill in some graphs. This is a great opportunity to think about how when we have constant acceleration, in this case gravity, that's going to lead to linear velocity and is going to lead to parabolic position. Okay? Parabolic vertical position. All right? So let's take a look here. So unfortunately, I actually made a mistake and wrote this as x. You should imagine it as y, but it's just displacement, okay? But usually we use x for horizontal displacement, okay? So the idea here is we're going to imagine shooting a bullet up, straight up from the ground, and then having it land back on the ground. So the idea is that that would be parabolic motion. The ball comes up and comes back down, okay? It is moving at a slower rate near the top, and it's then faster both when it's initially launched or shot and when it's about to hit the ground on the way back down. Okay, no air resistance here. What does velocity look like? Well, we put 0 in the middle. We'd have the initial velocity. The velocity would linearly decrease, become 0 at the exact moment that coincides to the maximum vertical displacement, and then it would just linearly decrease until it got to negative v naught. And the negative v naught would coincide with the time that it returned to its original vertical position. Acceleration is really easy. It's just constant. Put the 0 up here, define acceleration is negative g, negative 9.8. So somewhere below the 0 point, right? And it's just a horizontal line because it's constant. It is not a function of time. Okay? Now, why is it negative? Well, because I already defined my upward initial velocity as positive, so I must define gravity as negative. I just want to stress the fact that there's nothing sacred about g being negative. It's just being consistent with a coordinate system, okay? With a very common coordinate system. Up is positive. Excuse me. All right. So in question 2, the only difference here is we're going to, instead of shooting something up, having it come up and then, or reach a maximum height and come back down, instead, we're going to drop something off a cliff. What does that look like? Okay. Well, when you drop something off a cliff, the initial velocity should be 0, which means the slope of the tangent line of the initial curve, the parabolic curve, has to be flat. And then the rest of it is just half a parabola. Okay. The 0 point represents the ground. What's the velocity going to look like? Well, it's going to look similar. It's going to be linearly decreasing, but instead of starting at v naught, it's going to start at 0. Okay, and it's just going to grow down. Okay, so it's going to become larger in magnitude, increasingly negative, linearly decreasing. Okay, and the acceleration is exactly the same. Right, the acceleration is truly universal. Doesn't matter if you're throwing something up, dropping it down, throwing it side to side, but that's in the next chapter. The acceleration is always down, always constant. Okay, so here. Complete the vertical position, velocity, and acceleration graphs as a function of time for a pebble that is thrown, notice not dropped, but thrown, off the edge of a cliff starting with a downward velocity. All right, so we're throwing something down. What's that going to look like? Well, think about the tangent line. The initial tangent line can't be 0 anymore. It's got to be sloped down. So essentially what we're doing is we're taking this half parabola and we're shifting it a little bit to the left and then starting the shifted parabola on that vertical axis, like that. Right? So all I've done is just cut. I literally cut and paste the drawing, and then just erased whatever was behind t equals 0. Okay, whatever is to the left of t equals 0. So it's like a third of a parabola now. Okay, notice that that initial tangent line can't be horizontal because it has a initial negative velocity, which we see in the next graph as well. Right, so we still have something that's linearly decreasing, but it doesn't start at 0 anymore. It starts below 0 because it has an initial negative velocity. What about acceleration? Well, of course, just the same thing. All right? Okay, let's look at a problem here. A person stands on the edge of a building at a height of 212 meters and throws a ball straight up with an initial velocity. What is the ball's maximum height? Okay, that's going to be relative to the ground. At what moments, known as moments, after the toss does the ball achieve a height of 222 meters? If there's going to be more than one time solution, you better expect us to use the quadratic equation. Yeah. Okay, we're going to solve for t. And then part C, how fast is the ball traveling when it hits the ground? Okay, so here's the picture. Right, here we got the building, person standing at the top, throws the ball up, reaches that maximum height, measured from the ground, which is defined as y equals 0, right, comes back down. You get the gist of it. Okay, so we first want to find the time to the top. Okay, so we're just going to use this velocity equation where we know it's momentarily at rest at the top in order to solve for t. That gives us 1.71 seconds. So it takes 1.71 seconds to go from here up to here. Okay, and now we're just going to find the position by using that time. So it's a two-step process. All right, so then I'm going to take the time, plug it into the position function, make sure I have my initial position, which is 212 meters, right, relative to the ground, plug in everything else, get a maximum height of 226. So the ball goes up an additional 14 meters. All right, part B, at what moments after the toss does the ball achieve a height of 222? Okay, well then just write out the position function. All right, put 222 as the desired position, and then solve for t. Of course, it shows up twice. Oh, that's a typo. I should just say t. Sorry about that. All right, use the quadratic equation. Here's the correct quadratic equation, of course, because this is supposed to be linear, not quadratic. All right, and what do we get? We get two solutions, 0.767 seconds and 2.66 seconds. The first one's really small because it is already near 222. That's on the way up. It only takes 7/10 of a second, almost 8/10 of a second. But then it takes over 2.5 seconds to get back there because essentially we're asking for the time it passes through that line. So once on the way up and then once on the way down. Okay, so those are our two times it passes. A height of 222 meters measured relative to the ground. Finally, how fast is the ball traveling when it hits the ground? All right, so now we're going to use the kinematic equation, specialized for free fall, but the one that has velocity as a function of acceleration and displacement, because we don't really care about time in this case, because we have everything and we don't need time. All right, so now I'm just going to solve for velocity. Remember, it's plus or minus, okay? And I got my initial velocity, which is positive, okay? And I also didn't take any shortcuts here, like I did before, and have it, imagine it starting at rest from the top. I could have, but I said, well, I don't have to do that. I'm just going to just solve it. And I end up with a value of negative 66.6 meters per second. Right, now notice when I do the square root, I have a plus or minus. Both could be solutions, but the only one that makes the only one that makes physical sense is the negative value, because it has to be traveling in the negative direction relative to our coordinate system when it hits the ground. Okay, there you go. Things you can solve for, right? So we got a couple more. I want to show you these two examples because they're really counterpoints to each other. They have a lot in common. They involve two stones that are arriving in the same place at the same time. In the one case, they're both traveling down. That's example 3. In example 4, one is traveling down and one is traveling up. And there's just really variations on the theme, but the values, the answers are very different, and kind of there's some important differences in how we solve them, even though they are similar in so many ways. It's really a testament to how small variations can really make you think when in the nature of these types of physical word problems. All right, so a person drops one stone off a 200-meter cliff and then, a second later, throws a second stone straight down off the same cliff. How fast must the person throw that second stone so that both stones arrive at the bottom of the cliff at the same time? Okay, so we need them to both be in the same place at the same time. Okay, so the position functions for the stones are 0 equals y naught minus 1/2 gt squared for the dropped stone. All right, because notice that this is the position function equation and it doesn't have the plus v naught t term because v naught is 0. Meanwhile, and for the thrown stone, we would have a different position equation. We would have a y naught, the same y naught, which is going to be 200. We are going to have an initial velocity, and notice I'm replacing the variable t with t minus 1. That's because I know there's a 1 second delay. That way, I can solve t from the first equation, plug that t into the second equation, and already have it ready to go because I know how the two times relate. I could call this t2, and somewhere say that, oh, t2 is just equal to t1 minus 1 second, but instead I kind of substituted it in, okay? So we can then use the first equation to find t, as I said. So we're going to go ahead and do that. We're going to use the drop stone equation to find t. So we find the drop stone takes a total of 6.38 seconds to fall the 200 meters to the ground. Okay, well that means that the thrown stone has 5.38 seconds to catch up, right? So we're going to plug that in. I've already subtracted 1 from both times it showed up. So I subtracted 1 to get 5.38 there, subtracted 1 second to get 5.38 there, and of course I'm remembering to square it because it's 1/2 gt squared. Now unknown is v naught, so I'm going to solve for v naught. All right, and notice here that I left it as a plus. So when I solve for v naught, I'm going to get it with its sign. Its sign better be negative because it better agree with the direction of gravity, because the only way it's going to catch up is if I throw the stone down, of course. And I do. I get negative 10.7 meters per second. That's how fast we have to throw the second stone that was thrown a second later in order for it to catch up for this particular height cliff. If we change the height of the cliff, it'd be a different time. and thus would be a different initial velocity required to catch up. If we wanted to catch up halfway down the cliff, that'd also be a different problem. Speaking about halfway down the cliff, let's look at example 4. A person drops one stone off a 200-meter cliff. Oh, that sounds similar. And then a second later, another person throws a second stone straight up. Oh, that's different. From the base of the same cliff. How fast must the person throw that second stone so the stones meet in the midpoint? Okay, so of course we have to decipher this information, kind of think about what's happening here. So let's look. So start with the position function of the drop stone to find the time for it to reach the midpoint. Okay, fair enough, right? So I have my final position is going to be 100 meters. My initial position is 200 meters. Defined both as positive because I'm defining the bottom of the cliff as y equals 0. And here's my gravitational acceleration, no initial velocity, solve for my time, 4.52 seconds. That's kind of cool to think about, right? It takes 4.52 seconds to go to the first 100 meters, but then it only takes 6.38 seconds to go 200 meters. 6.38 is definitely not twice as big as 4.52, but that's because position is not being covered linearly when you're accelerating. Right? If I wanted to know how long it took to go 300 meters, it would just be slightly bigger than 6.38, right? Parabolic growth. Anyway, side tangent aside, let's continue with the problem. So thus the upward thrown stone has a position function that must satisfy this, okay? With the same y, okay, a different y naught, all right? And then the same idea of t minus 1 as in example 3, okay? All right, let's go ahead and solve for it. So our y is going to be 100 meters. Of course, right? Because they do need to meet at the same y, the same position. Okay, we're going to plug in t minus 1, which is just going to be 4.52 minus 1, which becomes 3.52. And we're just going to solve for v naught. Okay, and this time we solve for v naught, and we get a positive value, of course, because it's up. That's the only way this would work. And it's much larger, right? Because first of all, they're meeting somewhere sooner. And second of all, the thrown stone is working against gravity, whereas before the thrown stone had gravity to assist it catch up. All right. Pretty cool. Here's the one with sound. This is probably easier than the previous two problems. If you drop a stone down a well that is 120 meters deep and sound is assumed to travel at a speed of 340 meters per second, sound is a constant velocity phenomenon. Sound doesn't accelerate. Then how long after the moment you drop the stone do you hear the splash? We'll actually talk about the physics of sound at the very last chapter this semester. So something to look forward to. But for now, it's just constant velocity. That's all we need to know. So here's the idea. There's a certain time for the ball to fall down while accelerated by gravity, and then there's the time for the sound to travel back up at a constant velocity. Okay, both the travel distances are 120 meters. Okay, our coordinate system is such that positive y is up, and 120 is the top, and 0 is the bottom. Okay, and v naught is 0 because the stone is dropped. All right, so t fall is found using the position equation, which simplifies quite a bit, right? Because of course v naught is 0, so we just have a 0, and we just solve for t, simply 4.9 seconds. 4.9 seconds is how long it takes to fall 120 meters. Is that consistent? Oh yeah, because it took 4.52 seconds to fall 100 meters. Oh, there you go. Right? Did the check, right? Make sure we're not making a calculator error. All right, so carrying on. Then we're going to find, we know the velocity of sound by definition is just a vertical position, in this case, divided by time. If we want to solve for t, then it's just going to be distance over velocity. And well, that means the sound takes 0.35 seconds to travel 120 meters. So we just add the two times together. And so then the person will hear the splash after dropping the ball 5.3 seconds later. Okay, most of that time is actually the time to fall. The sound is relatively fast because it's so fast, right? At 340, right? All right. Here are some examples that you can do on your own. Good selection of further examples. Plenty from this chapter, as will be the case certainly as we move forward. Right, a lot of really kind of chunky content in these chapters. And I thank you so much, for watching this video. I hope it's been really helpful and kind of gives you some further practice about what constant acceleration is all about. And we're really going to have a chance to continue to dig into that in the next chapter, where we just combine free fall with side-to-side motion, which you've started to see if you started on the lab. Projectile motion, it's called. Okay? All right. Thanks again for watching.